And I just want to remind folks that our for today's talks, to try to keep things running smoothly, please try to keep your audio muted unless you are actively talking and or clapping. Feel free to have your video on or off. It's totally up to you. If you want to ask questions during the talks, please add them to the chat throughout, or use the raise hand feature at the end and wait to be called upon. I've told our speakers that they should ignore the chat during their talks, so feel free to have whatever conversations you want to have going on there, and then we'll raise those all up to conversations at the end of their talks. And of course, just in general, as in all settings, please be friendly, courteous, and respectful of everyone here. I also want to take a brief moment to advertise that we're hoping to continue this talk series into the fall. And our plan right now is to keep it at the same time as something that broadly works for a lot of time zones. So right now, every other Wednesdays at this time. If you really want to make it and you can't make that time, please let me know. And if we hear a lot of complaints, we'll try to adjust it. But we may have to go on a semester by semester schedule here. So to help support that, please submit abstracts or encourage other scientists you know to submit abstracts for talks at our website. There's a nice form there where you can submit things there. And everyone can submit abstracts, but I'll say that we'll also continue to prioritize making this a space for junior scientists to be able to share their work, especially important now because it's so hard for all of us to travel. And junior scientists give really good talks. Okay, so I am going to stop sharing, and let's start with Johanna Voss. Voss or Vos? Am I pronouncing your name?
Voss.
Totally wrong.
Yeah,
Voss.
You got it right.
Thank you. From the American Museum of Natural History. Go ahead and take it away.
Great, thank you. Okay, is everything showing up okay? Right.
Yeah.
Okay. So, well, first I just want to start by thanking the organizers for setting up this seminar series, which has been really, really nice while we're all working from home and feeling slightly isolated. But today I'm going to talk about probing cloudy brown dwarf atmospheres with variability monitoring and offer some lessons for the JWST era. So let's get started. So brown dwarfs have temperatures below about 2,200 Kelvin, with L dwarfs being the hottest. T dwarfs are cooler at about 1,200 Kelvin, and Y dwarfs are the coldest objects we know of. The coldest Y dwarf we know of has a temperature of about 250 Kelvin. And these temperatures overlap with the temperatures of the directly imaged exoplanets. So they really inform how we interpret their observational properties too. And depending on what pressures and temperatures exist in the atmosphere at these different spectral types, different species can condense to form clouds. So you get silicate and iron clouds in L dwarfs. In the T dwarfs, you don't get as many clouds, but you can get salt and sulfide clouds. And cooler again, for the Y dwarfs, you get water and ammonia clouds in their atmospheres. And these clouds have a really huge effect on their emergent spectra, and they really shape our observations. So it's very, very important that we really understand these clouds to the best of our ability. And one way of probing these clouds is through variability monitoring. I think my video is not playing, I'll try again. Where we measure the brightness over time and look for fluctuations arising from patchy condensate clouds rotating in and out of view. And this technique is super powerful for understanding brown dwarf and giant exoplanet atmospheres. And I know that not every exoplanet subfield loves clouds as much as we do. So I'm going to really quickly go through some reasons that we jump for joy when we detect cloud-driven variability in brown dwarf atmospheres. And I don't have time at all to go into any depth for these techniques, but I encourage you to reach out to me afterwards or look up the papers that I'm about to reference if you want to learn more. And so the first reason we jump for joy is that we can create spatial cloud maps of variable brown dwarfs using either Doppler imaging or light curve inversion techniques. The second reason is that multi-wavelength light curves can help us to identify multiple cloud layers, revealing the vertical cloud structure in the atmosphere. And the third reason is that looking at the wavelength dependence of the variability amplitude through spectroscopic variability monitoring will help us to understand the size of cloud particles that are actually causing your variability. And finally, the last technique I'll just highlight is a brand new technique we just published this year. If you can find a cool brown dwarf or giant exoplanet that is both variable in the infrared from clouds and emits in the radio, you can combine these measurements to actually measure the wind speed of the atmosphere. So once you detect variability in your favorite brown dwarf, your favorite free-floating planetary mass object, or your favorite directly imaged exoplanet, it opens up a whole new range of possibilities for exploring the atmosphere. And with that in mind, I've spent the last couple of years trying to understand the variability properties of a sample of exoplanet analogs so that we have some expectation of what we will find for the directly imaged exoplanets with JWST. So first I'll explain what I mean by these exoplanet analogs. So here I'm showing you field brown dwarfs on a color magnitude diagram. And they follow this well-trodden path as they cool from M to L, getting redder and redder, followed by this kind of dramatic blueward shift for the T dwarfs. And in recent years, a population of young, low-gravity brown dwarfs have been discovered and characterized. And they form this distinct sequence compared to the high-gravity field brown dwarfs. They're consistently redder and less luminous than the field brown dwarf population. And these differences between the young population and the field population is generally explained in the models by thicker clouds that form higher in the atmosphere, as well as non-equilibrium chemistry. And both of these things are arising from the lower surface gravity of these objects. So that means when we highlight the population of directly imaged exoplanets, you find that the L-type exoplanets exhibit the same, or they fill the same color magnitude space as these low gravity objects. Their colors, spectra, and even their fundamental properties, such as age, temperature, and mass, are all remarkably similar. So the much easier to observe free-floating objects serve as an excellent analog for the directly imaged exoplanets. And because we think that the cloud properties in the atmosphere are responsible for the differences between these two samples, it is reasonable to expect that the variability properties will be different too. And we've seen some hints of this already. So there is a small but growing number of low gravity, young brown dwarfs that have very large variability amplitudes in the near infrared, and 3 of which I'm showing here. Additionally, in 2019, I carried out a variability survey for variability in the J band in low gravity L dwarfs. And we found that these low gravity objects were nearly 3 times more likely to be variable compared to the field brown dwarfs. But today I'm going to talk about a paper that just came out last month where we monitored 3 young low gravity L-type brown dwarfs for variability with Spitzer, so moving into the mid-infrared. And all 3 targets have estimated masses of about 20 Jupiter masses. We observed in both channel 1 and channel 2, and we detected honestly very, very low amplitude variability in these 2 objects and did not detect variability in the 3rd object. So the top panels here are showing you the light curves for our 2 variable objects. The bottom panel shows the periodic method we used to detect significant variability. But we also combined this with a Bayesian information criterion to identify which objects were significantly variable, so we could be confident about these super low amplitude detections. And for this work, we compiled all of the Spitzer variability data in the literature for young and field brown dwarfs. So here I'm showing you all brown dwarfs that have been monitored at 3.6 micron on the left and 4.5 micron on the right. The symbol size corresponds to the variability amplitude that was measured. Field objects are shown in blue and low gravity objects are shown in pink. The darker colors represent actual detections and their measured amplitudes, and lighter colors represent upper limits on the amplitudes. So as you can see, we actually have a decent sample size now to explore the variability properties of these different populations. So the first thing we looked at was the variability amplitude of the low gravity and field samples. And again, low gravity objects are pink and higher gravity objects are in blue. And right away, we see that there is this enhancement in amplitude for late L objects at 4.5 micron. So these late L objects have amplitudes much higher than field late L objects and also much higher than any early L dwarfs, whether they're young or field. And we don't see the same enhancement at 3.6 micron, but I wouldn't give up on 3.6 micron just yet because we haven't, if you look closely at this plot, you'll see that we just haven't observed the same objects in these two to make this comparison. So we actually just need a bigger sample size at 3.6 micron to definitively explore whether we're going to see the same enhancement at 3.6. And as luck would have it, I'm actually currently analyzing a load of 3.6 micron Spitzer data for a large survey. So I should be able to answer this question very soon. The other thing we can measure is rotation rates for brown dwarfs as a function of age. So I made this plot by combining a lot of different surveys, and you can see that the brown dwarfs spin up over time as they contract. So the complete opposite to stars. And the various lines overplotted here constitute theoretical upper and lower limits for the rotation period over time. So the red lines show the breakup periods for a 10 and 84 Jupiter mass object. The black lines here show the periods expected from angular momentum conservation, again for a 10 and 84 Jupiter mass object. And to do this angular momentum conservation calculation, we essentially have to tie the initial angular momentum to the highest and lowest rotation periods in our first age bin. So that's why there's two sets of the black lines. And we find that the brown dwarfs, their periods generally do fall between these limits. Nothing is rotating faster than the breakup period, and nothing is rotating slower than angular momentum conservation would expect. And finally, we can also measure the inclination angles of a sample of brown dwarfs. So on the left here, I'm showing you a beautiful high resolution spectrum taken with Gemini Juniors. The data is shown in black and our forward model is shown in red. And we use this to measure the rotational velocity, or V sin I, of a sample of brown dwarfs with measured rotation periods. And for each brown dwarf, we can combine the V sin I with its rotation period and a radius estimate to give the viewing angle of each brown dwarf. And we find some pretty interesting results. The first is that our observed variability amplitude is limited by the viewing angle of the brown dwarf. So the highest variability amplitudes that we have observed are in objects inclined close to equator on, or 90 degrees in this plot. The maximum amplitude observed at each inclination then falls as the object is inclined closer to pole on. And then finally, we don't even have any variability detections below about 20 degrees. And this makes sense and can be explained geometrically. If a cloud is rotating about the equator, you'll see it if you're looking at the equator, and you won't see anything if you're looking pole on. And this is true for both the Spitzer band passes, and we also found this with a smaller sample in 2017 in the J band. The second interesting trend is that the inclination angle appears to be correlated with J minus K color anomaly, both for the young and field objects. The J-K color anomaly is defined as the difference between an object's color and the median color for that spectral type and gravity class. So any object with a positive color anomaly on the right-hand side of the plot appears redder than the median. An object with a negative color anomaly appear bluer than the median on the left side of the plot. And based on this figure, we find that objects that are viewed equator on or at 90 degrees appear redder than the median, and objects viewed pole on appear slightly bluer than the median. And this could be explained by considering an inhomogeneous latitudinal distribution of clouds. So if clouds were thicker at the equator relative to the poles, it could result in redder colors for the equator on objects. And we don't have to rely on my keynote simulation anymore, because in recent work led by Johanna, they've actually been looking at the effects of rotation on the dynamics of clouds using 3D GCM simulations. Excuse me. The color here is representing the outgoing thermal radiation flux at the top of the atmosphere. And this plot shows that the pole is typically brighter than the equator, which is a result of thinner clouds at the pole and thicker clouds at lower latitudes at the equator. And you can see by the different cases I'm showing here that this effect is particularly strong for the faster rotators. And every time I talk about inclinations, I feel like I have to show these amazing images of Jupiter. So I think about 3 years ago at this stage, the Juno mission revealed Jupiter's poles for the first time, showing that they are very, very different to the thick equatorial bands that we observe at the equator. And we're not going to be able to resolve a brown dwarf or a giant exoplanet anytime soon, but we might be seeing the first glimpses of this phenomenon in brown dwarf atmospheres today. And I'd like to end this talk by looking forward to JWST. The brown dwarf community has done a lot of work on brown dwarf variability over many, many years. And this means that we are fully ready to move on to detecting variability in the directly imaged exoplanets with JWST. We have all the tools ready to go, and we have learned some valuable lessons from the free-floating planetary mass objects. And lesson one is good news. It's that the directly imaged planets are very likely to be variable. In the near infrared, we have evidence of a higher variability occurrence rate for low gravity objects compared to higher mass brown dwarfs. And we specifically see very high amplitudes at spectral types of around like late L, L7. And so that's actually exactly where the HR 8799 planets lie. However, the second lesson is that the viewing angle really matters. So while I think that it's very likely that the HR 8799 planets are highly variable, they're also probably inclined pole on. So we may be unable to actually detect that variability. And for this reason, I think we may be better off targeting an exoplanet that is likely inclined equator on, such as Beta Pic B, which I'm showing here, even though it may not be at this sweet spot for very high amplitudes. And lesson three may be more my personal feelings than an objective fact, but I think that it will be worth it. If we can detect variability in a directly imaged exoplanet, it will open up a whole new range of characterization possibilities for that exoplanet. We can start to make spatial maps, explore the vertical cloud structures, and maybe even measure the winds on these distant worlds. So I'll leave it at that. Thank you so much for taking the time to listen today, and I would be more than happy to take your questions.
All right, let's thank Johanna again, or for the first time. Bravo! So I'll remind folks, if you have questions, please either go to the participants tab and use the raise hand button to raise your hand to ask a question, or go ahead and type it in the chat. And we'll let's start with Emily. Emily Rauscher, go ahead. What's your question?
Or you could start with Kevin. I think his question got in first.
Oh, fair. All right, let's start with Kevin. Kevin, let's start with you. Thanks.
Okay, since I can't raise my hand, thank you. I wanted to know, in your opinion, what might be the best wavelength ranges for Webb to search for variability?
I think for searching for variability, we do see the highest amplitudes in the J band. So I think for searching, that will be very useful. However, I also think that looking in the mid-infrared, about 10 micron, which is an area we actually haven't been able to look at for variability, will reveal a lot of information, because that's exactly where the silicate scattering feature is. So maybe, on a searching for variability, we should maybe focus on the J band, and then once we've detected variability in a particular object, we could move to the mid-infrared to try and understand the clouds themselves.
All right, now Emily, and then we'll do Everett after.
Wonderful talk. I love this science so much. My question is, I love all your lessons. I agree with all your points. I'm trying to remember what system it was that Marta Bryan recently led the measurements to get all the different angles of the system. Because
mass 0122.
Because I don't remember what the orientation of the planet was relative to us, but I'm wondering whether that might, based on these results, be a good target for variability or not.
Yeah, so I think that is a great target. The only problem with that target is the detection of variability isn't 100% sound. They weren't completely sure. If you look at the variability paper, it's just not a huge amplitude. One object that I think has to be done immediately is VHS 1256, which is this absolutely monster variable, and it's a companion exoplanet too. So I think that could be our first foray into direct imaging with JWST.
Cool, thank you.
Everett, go ahead.
Excellent talk. Just a similar question to Kevin. I was wondering which mode. There's many different possibilities, like direct imaging, coronography, near spec, using, putting up the mass. I was wondering if you have a favorite mode for a system like Beta Pic that you think would work.
I'm not sure. So for Beta Pic, it's so hard to do because it's going to be really close to its host star. So I think, coronography and doing photometric variability monitoring is the way to go. For the further out objects like VHS 1256b, I think you don't need to use a coronagraph. And then I would love to use NIRSpec with the multi-wavelength simultaneous monitoring. I think that would be so excellent for this because, looking at the near infrared and the slightly mid-infrared at the same time is so informative about the cloud structure.
Thank you.
Awesome, thank you. In the interest of time, I want us to move along to Daniella's talk. James, please feel free to type your question in the chat, and maybe Johanna go through, and there are a few questions in the chat that maybe you can address as well. And we've also asked both of our speakers that in addition to kind of questions at the end, they're able to stick around a little bit longer after the end of the hour too, so we can have a more informal discussion there. So let's thank Johanna again for a lovely talk. And then our next speaker is Daniella Bardalez Gagliuffi, sorry, who will be talking about binaries or variables. So Daniella, go ahead and share your screen and take it away.
Thank you. All right, there we go.
Looks good.
Thanks a lot, Zach and all the organizers. And I agree with Johanna, this series of talks are making me feel like there's still a community outside of my window, so that's nice. And I'd like to share the work that Afra Ashraf is doing. She's an undergrad working with me. She's a senior at Barnard, so she will be applying for grad school this round, so pay close attention. And then continuing on the topic of target prioritization for JWST, I'm going to present the work that Afra has been doing with me. So Johanna gave a great introduction to what I'm about to talk about. Brown dwarfs experience weather patterns, much like exoplanets. They experience weather, climate, wind speeds can be measured now. So it's, we have a really good prior for exoplanet atmospheres that we can start studying in brown dwarfs. Brown dwarfs have effective temperatures between 2400 Kelvin and 250 Kelvin, the coldest one known. And because of that, those cool temperatures, these are prime locations for the formation of clouds of silicates and iron. And clouds are not homogeneously covering the brown dwarf. They have patches. And these patches cause the variability that we observe. So patch clouds and rotation are the cause of variable light curves. The most inclement weather, however, happens around the LT transition, right here. So the LT transition is roughly between 1000 Kelvin to 1400 Kelvin. This is a region in the brown dwarf evolution where because brown dwarfs get cool over time, since they cannot sustain hydrogen fusion, they actually go through these temperatures and get cooler over time. And their spectra, their atmosphere changes and their emergent spectra changes as a consequence. This region, and actually the entire brown dwarf regime in terms of temperatures, is shared by all sorts of giant planets. Jupiter's at the hotter end. Old giant planets will be as cold as white dwarfs. So again, studying brown dwarfs is an excellent primer to study planet atmospheres later on in more detail. So the main characteristic of this LT transition is brightening in the J band. So as we can see here, we believe that L dwarfs have clouds made out of silicates and iron and oxides, and that after, as brown dwarfs get cooler over time, as they go through this LT transition, these clouds are, they sink below the photosphere. Some call it rainout, some call it sinking below the photosphere. And then this allows us to see at the top of the atmosphere methane gas, which shapes the spectrum of T dwarfs dramatically. And models have a hard time reproducing these spectra because clouds are really hard to model. And there's some improvements, for example, by Diana Powell, where she's trying to include microphysics in cloud modeling, which makes it even more complicated, but at least somebody's taken the lead on that. After the rain out, these atmospheres look clear on the T dwarfs, and then by the white dwarfs, all hell breaks loose, and apparently there's clouds again, possibly of water. There's some indications of that. An alternative explanation for this atmospheric dynamics is an alternative explanation to clouds altogether, proposed by Pascal Tremblin a few years ago, was that instead of having clouds, we could have the type of convection that happens on the Earth's oceans and also between the mantle and the core. And it's due to the slow reactions between CH4 and CO, and also between ammonia and nitrogen and molecular nitrogen. So that allows some patches of the surface of brown dwarfs to have different temperatures as the bottom. So due to these extreme atmospheric dynamics, it's no surprise that the highest variability we find in brown dwarfs is around the LT transition as well. On this study, Jackie Radigan found that 9 out of 57 objects that she surveyed were found to be likely very significantly variable, including our star 2139, which is the most variable brown dwarf known to date, with a 27% amplitude in the J-band. This was a ground-based survey, and as I mentioned, it's 9 out of 57 objects that had to be surveyed in order to find variability. Sorry, 57 objects that had to be surveyed in order to find 9 to be variable. So this is really important work, and these are very time resource intensive observations that end up, sometimes as possibly because of viewing angle, we just cannot measure variability. And that is a sad use of telescope time, sadly. However, in a past life, 2139 was a spectral binary candidate. Back in 2010, Adam Brigasser and collaborators identified this peculiar spectrum to be the blended light combination of two other templates, two other single templates of brown dwarfs. So they thought that this 2139 object was actually the mix of an L9 and a T4, two separate brown dwarfs whose that are closely separated in angular space, so that we get one unresolved spectrum that looks peculiar because it's a mix of both. But neither high resolution nor imaging nor RV could resolve this object. Daniella Pai went off and got HST images for this object and couldn't resolve any companion down to a difference of 3 magnitudes. And Harish Kandrika and collaborators also figured out that the radial velocity monitoring yielded a stable radial velocity. So that's, yeah, so it was unclear what was going on with this object. It was also the case of 1324, which is a member of AB Doradus. It's a young T2 dwarf. And also back in 2010, this object was a spectral binary candidate. They thought that this spectrum was the blend of also a T9, an L9, and a T4. And so the addition of the two independent spectra would yield an object, a spectrum that is peculiar in very particular places. This object turns out to be variable, and it has a very strong variability shown in this light curve on the right. And so like these, there have been a few studies that have found some spectral binary candidates to be, in fact, single photometrically variable objects. There's Harish, Jackie Radigan's, and then Elena Mancavacas recently in her Cloud Atlas paper decided to measure indices from both Brigasser 2010 and my spectral binary paper 2014, and then try to see what she found, because there was enough indication from previous studies that this indices could be related to variability as well. And what she found was that, I don't remember the numbers correctly, Elena can answer this, but she found a significant number of her variables had the spectral indices measured consistent to be a spectral binary candidate. But none of them were over luminous. So that's how we thought that, okay, well, that's how they thought that these are most likely not binaries, just single objects which are variable. So what's going on? It appears that blended light atmospheres can occur due to two objects with independent, with independent atmospheres. They are closely separated in space, so our spectrograph doesn't resolve them into two objects, so we get one peculiar spectrum, or that we have one single object with a patchy upper layer of atmosphere that allows us to see the hotter bottom layer. Bonus case, we have a band-like structure on the surface of the atmosphere, so that we are essentially seeing two different temperature spectra combined. Both of these cases, 3 of these cases, can produce peculiar spectra. The current technique that we have to identify spectral binary candidates consists of 2 steps. We first measure spectral indices across the spectrum, and then compare the indices against each other and see how many times they fall in these selection regions. After we find our candidates from spectral indices, we compare the spectra to single and binary templates made out of real spectra. These are not models. And then we evaluate a hypothesis test to see if the binary hypothesis is a more likely one than the single one. And this is how we get a spectral binary candidate. And then we go and get a high resolution follow-up, either imaging or astrometry or RV monitoring, to confirm that that object is in fact, that source is in fact a binary system. So we can reproduce this technique, but instead to find variables rather than binaries. So in order to, because let's be honest, JWST is not going to give us 20 hours of monitoring time per target for each one of our variables. So this is what we're going to do. In order to predict variability, which is a time-dependent effect from single epoch spectra, slow resolution, we are following the same steps that we did in order to identify the spectral binaries in the first place. So we're focusing first on the LT transition that has the most variable roundworks. And we selected 198 spectra from 160 unique objects from the Specs Present library. All of these spectra was acquired. It's all in Prism mode, so it's acquired all at the same time. All the orders, there's no orders. It's one-shot spectrum. It's a low resolution spectra of about 120, like as low as you can go pretty much. And it is calibrated with A0 stars after you have taken the spectrum of the target. All of these spectra are archival. None of these were taken with the intention of measuring variability. All of these spectra were not time resolved. And we selected 17 benchmark variables, objects that have a variable light curve. And we ignored all upper limit variables. So we were being very, very conservative with our selection of benchmarks. And with those 17 objects, we found their spectra on the Specs Present library. Again, the spectra was taken one day, you know. What we're seeing is essentially the integrated light of, 40 minutes of observation, roughly. We're not seeing single shot, like couple minutes spectra. So we measured indices, the original indices from the Burgasser 2010 study and my study from 2014. And then after compare these indices against each other and selected 11 index parameters that separate known variables that are shown in these images in red. Those are the red stars that separated those stars from the rest of the library, and particularly from the known spectral binaries that are the blue triangles. All the objects, and then this is how we designed the regions to try to cluster as many known variables as we could. And we have, like, by comparing these indices and these 11 index parameters, we find now 33 variability candidates that we will follow up with photometric monitoring. We have decided to call a candidate any object that falls into these regions more than 9 times, which is where the first known variable resides. And so in the left 2 plots, the green circles are our variability candidates. And as you see, they cluster pretty well with the rest of known variables. We also, if you look at the histogram on the right, managed to not include any known confirmed spectral binary. Those are all, that's the blue column. All of those confirmed spectral binaries are never found in one of these regions. And in green on the histogram on the right, we can see the known not variables. This is confusing. The known not variables are objects with a flat light curve, or with an upper limit on variability, but essentially not a secure variability detection. So these regions are successful at not selecting these objects that are not variable as far as we know. And Afra is preparing this work for publication in the next few months. So next few months though, but yeah, keep your eye up on the archive. So what are the indices measuring? I think this is the most puzzling part of the whole project, because we have a technique that seems to be working, and we're trying to understand what physical parameters we're actually probing. So here I'm showing where all the indices are measuring flux. Indices, these spectral indices are ratios of integrated flux in very short ranges of wavelength. And what we're seeing is essentially, we are probing all 3 bands in the near infrared, but we're probing at different places. All of these indices were created in order to highlight in the numerator some part of the spectrum that seem to be different in spectral binaries compared to their best fit single template. Whereas the denominator was a part of the spectrum that always seemed to be stable no matter whether it was a spectral binary or not. So this is how they were created. And we seem to be finding a complex mixed signature of atmospheric chemistry, clouds at different altitudes, maybe inclination angle as well. So definitely more research is needed in order to figure this out. And as a 0th order approach, we tried measuring the Pearson correlation index. 1 in red tells you that the 2 quantities are perfectly linear correlated, and blue is perfectly linear anti-correlated. So it's very possible that all of these indices are having nonlinear relationships with the physical properties, but we're starting to see some relation. We're trying to figure out essentially what are the relationships between these indices and their ability to predict physical properties of the objects themselves, just based on archival data. And as a proof of concept, there is at least one object that happened to be in Johanna and Jackie Flaherty's low gravity variability survey with Spitzer. This object that I have covered his identity to cover his privacy is one of the variable candidates from Afra's study, and we just happened to find it also in the variability survey that Johanna and Jackie were carrying out. So this is really exciting because it's indicative that we're definitely identifying signatures of positive variability. We're definitely identifying signatures of blended light atmospheres. As I showed the banded little cartoon earlier, that kind of object wouldn't necessarily produce a variable light curve, but then we could be predicting banded structure. So this is still kind of a new avenue that we're exploring, but some things to remember is that we have designed a technique that predicts cloud-driven variability before spending all this time on resolved photometric observations. So that means that this technique will help us prioritize target for JWST, where time is going to be precious. The next step is to launch a ground-based variability to confirm the candidates. The next step is to apply this technique to irradiated brown dwarfs to try it first, and then hot Jupiter transit spectra. Because of course, with the hot Jupiters, we have a much more similar atmosphere as an irradiated brown dwarf, which are very different from the isolated ones. But that is an interesting direction in which we can study planet weather. And even more in the future, once we understand what are the correlations between these indices and the physical properties that they're probing, we can improve global circulation models by adding information to the degenerate inverse problem of surface mapping. Because either we're looking deeper into the atmosphere in the Z direction, or we are seeing bands around the brown dwarf. And that gives us a lot of information in order to invert light curves and produce a map of the surface of the atmosphere. And finally, Afra Ashraf is going to a grad school near you, so keep your eyes open for an amazing grad school application. And I want to take a couple minutes to advertise my Cosmomotas project. I am partnering with another postdoc from the ESO, in Garching. Her name is Gabriela Calistro Rivera. She works on galaxies and AGN, and we're both Peruvian, and we are, it's probably rescheduled for March, but we're gonna have a workshop in Huancayo, which is in the highlands of Peru, to train teachers about astronomy so they can then take astronomy into their math and physics classes, and then start these astro clubs where kids can have astronomy as an extracurricular and trying to promote astronomy in Peru. So if you have a minute to check out our Facebook page, I appreciate that. Thank you. That's all I got.
Awesome. Let's thank Daniella for a great talk.
Thank you. And I'm glad an ambulance didn't just run by my window.
Perfect timing. All right, so if you have a question for Daniella, please raise your hand or drop a note into the chat, or just turn on your video and wave enthusiastically. I'm gonna, all right, I'll let Emily raise her hand first. Go ahead, Emily.
I mean, anybody else can go before me. I don't, like Caroline, go first.
All right, Caroline, you go first.
Okay, I have a quick question. I was just wondering whether the objects that are in your sample of potential new variables, I was wondering if they have distance measurements as well, because if we had the distance, we could also check to see if they're over luminous, like we might see for a binary where we have two objects contributing.
Yeah, that's a good point. Because these are LD transition objects, most of them don't have Gaia, but Will Best just published his big paper on parallaxes. So I expect that some of them do. I have to check with Afra. I think that, I believe that we have, at least for the 33, maybe half of them will have distance. Well, yeah, we'll absolutely check over luminosity, let you know.
Great, thanks.
Go for it, Emily.
Sorry, I always am too interested in these talks because they're wonderful.
It's a very good problem to have.
Very cool stuff. I'm also super curious about what these indices are telling us about what's going on in the atmosphere. Do you have plans to kind of use a grid of 1D models or something to interrogate kind of how the indices correlate with physical properties?
You mean like measuring indices on spectral models? Or
yeah, I'm wondering if you could take a bunch of simulated spectra from 1D models where all sorts of different parameters are varied that might be important, and then see kind of measure the indices for those models and see if they do point towards particular physical properties. Or maybe it could be more complicated, and maybe you're going to need to, if you just do one set of models, it doesn't make much sense, but maybe because, what you're pointing to is that this is, possibly seeing multiple spectral components, it might get really messy, and it might need to be like combinations of different atmospheric profiles or something.
Yeah, absolutely. That's a really good suggestion. The only catch is that, as I mentioned earlier, modeling L dwarfs in particular is very challenging because of the clouds. So I think it's an exercise that we should absolutely try and see what happens. Especially on the L dwarf side, I'm not entirely sure what care we need to take. But that is a really good point, and absolutely something we should check. Thank you.
I'm also curious about these the indices. I guess more on the observational side. Do we expect these indices to be the place where variability is strongest too? Like what do we expect for the variability of these indices? Are we seeing a signal here because that's like where a cloud clears and you see deeper and magic and stuff happens? Or are these like tracing something else that is like gravity that is then related to the likelihood of patchiness?
That is a really good
Any
point.
ideas?
That is the first thing that I thought. I thought that we were seeing, because that's what we do with spectral binaries, right? We just look at these very particular places in the spectrum, and we know that the peculiarities there are due to a blended light spectra. So that was my first hunch too. And I think that the answer is I don't know. I mean, they may be, the tricky part about this is that we are probing very specific parts of the spectrum, but we're possibly predicting global properties as well. And a gray cloud would change the whole spectrum at the same time, right? It makes the whole object redder, rather than changing particular places. So I've actually tried comparing a spectrum of a known variable to other spectral templates of the same spectral type, and it was difficult to see consistency. Also, we don't have a big enough sample. There's probably 1 or 2 known variables per spectral subtype. So it's not like we have many objects to see these very, very subtle changes in the spectra. So we need to do more research, and we need more variables in order to determine this. Sorry, Zach.
Sounds good.
Yeah.
Sounds good. All right, I don't see any more questions. So let's thank Daniella one more time.
Thank you.
And we'll call this the end of the talks for today. So please go ahead and go have lovely afternoons, especially Emily's child, whose face is like appearing and disappearing out of her virtual background. Go have a good afternoon, or whatever time it is wherever you are. We'll now transition to the like people gathering up their teacups and unplugging the projector moment. So feel free to stick around if you want to chat a little bit more.
Thank you.